Okay, we will now talk about section 6.2, which deals with transforming and combining random variables. A lot of these concepts we talked about earlier in the year, as far as transforming, combining, will be a new thing, and it leads to some nice little challenging problems that may be interesting for you. But first of all, in regards to transforming, we had these concepts earlier in the year. So let's talk about what it means in regards to transforming. So let's just say if you have a data set. Let's just make up a simple data set. So let's just say, for instance, 1, 2, 3, 4, 5, and 6. So that's our simple little data set. And we want to know our summary statistics. So we want to know the measures of center. The main one we have are, of course, the mean and the median. And the main ones of spread that we use are the standard deviation, the interquartile range, and the range. And, of course, I think you could easily find those with this data set by hand. The mean is just the average, and so that's when you average these numbers, it's 3.5. And this data set is perfectly symmetrical, and so its median is going to be the same as the mean. The median, of course, the number in the middle, and there's two numbers in the middle, 3 and 4, so we would average those two to get the median at 3.5. The range is easy to find. It's just the biggest numbers minus the smallest, so it's 6 minus 1, and it's 5. And the interquartile range, Q3 minus Q1. Q3 is just the median of the upper half of numbers, so it's 5. Q1 is the median of the lower half of numbers, it's 2. So this is 5 minus 2, which is 3. And then the standard deviation, we have a formula for the standard deviation that we could certainly use off of our formula sheet, but we'll just use our calculator to find that. And so what we'll do, and of course this will tell us the other summary stats as well, is I'll just enter these in list 1. So I hit Stat and Edit. And I've entered these numbers in list 1, 2, 3, 4, 5, and 6 right there. And so to get the summary stats, I just hit Stat, Calculate, one variable stats, just like we did in chapter 1. And I want list 1 there. So make sure the frequency list is blank or that it has a 1 in it. And then hit Calculate. And so my standard deviation is the S. That's the one that we use. It's 1.8708 approximately. So our standard deviation is equal to 1.8708. And so there's our measures of center. There's our measures of spread, our most popular ones. Now the question is, what happens when we transform our data? For instance, let's say, what happens if we multiply everything in the data set by 2? So that would be, we could call that random variable 2x. And so I just multiply every value by 2. And so that's going to be 2, 4, 6, 8, 10, and 12. What happens to our summary stats? First of all, for the measures of center, well, you notice the mean and median on this are now going to be 7. So our x bar, or our mu as we'll call it if it's a population value, would be 7. It is multiplied by 2, and so is the median. So it's multiplied by 2, just like the data set. Well, what about the measures of spread? Well, the range, the biggest minus the smallest, 12 minus 2. So our range is 12 minus 2 is 10. It got multiplied by 2. What about our IQR? Well, Q3 minus Q1. So median of the upper half of numbers is 10. Median of the lower half of numbers is 4. 10 minus 4 is 6. So our interquartile range, sort of a measure of what the middle 50% of the numbers is doing, is 6. It got doubled. And let's see what happens with the standard deviation. So if I go Stat, Edit, and I put 2x right there, which, by the way you could quickly do that, quickly doing operations here, if you just highlight the top of list 2 and then just go second 1, list 1 times 2, it just puts 2 times list 1 there. And so now I'll do the summary stats with those. So I hit Stat, Calculate, one variable stats of list 1. I'm sorry, I have list 2 now. So I'm working with list 2, and we go Calculate. And so now the standard deviation, as it turns out, and S is the one we use, 3.7417. So our standard deviation is 3.7417. And in fact, that is double that. So our generality is when you multiply a random variable values by a number, it multiplies all the measures of center and of spread by that number. And by the way, any number of placement as well, such as the 75th percentile or the 20th percentile or whatever. But what if you add or subtract something? Same thing applies here, by the way, if you divide. What if you, let's say, add 4 to all of these numbers? Well, x plus 4, we just add 4 to everything in x. And so that's going to be 5, 6, 7, 8, 9, and 10. So if we do that, so we would get, well, the mean's the number in the middle, and so so this would be, our x bar would be 7.5. That's just the number in the middle, and so that is our median as well. So when you add 4 to a data set, it also adds 4 to the measures of center. What happens to the measures of spread, though? Well, the range, the biggest minus the smallest, 10 minus 5, it's 5. It is unchanged from the original range. What about the IQR, Q3 minus Q1? Well, that's going to be 9 minus 6, or 3. It is unchanged. And if we did the standard deviation, so if I look that up right quick, so if I go stat and edit, and in list 3, I just added 4 to everything in list 1, so I go second list 1 plus 4 down in the command line there. So it puts my numbers there. Now if I do stat, calculate one variable stats of list 3 to tell me my summary stats, and there's my standard deviation, 1.8708, the exact same, 1.8708, the exact same as it was before. So, and you could also do, if you think about this graph, so our generality is, if you multiply a distribution by a value, it multiplies all the measures of spread and of center. But if you add or subtract something, then it just affects the measures of center, not the measure of spread. And if you were to, let's make a quick graph, and I think that'll also communicate this. And so if we did a graph, and I wanted to do this kind of neatly on some graph paper, but I forgot to bring it. So I'll just try to draw this neatly to demonstrate it. And so if we go, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so the original data set X is just 1, 2, 3, 4, 5, and 6. And then 2x, let's see what happens with 2x. So you can see how they vary. So if you go 2x, well, if you do that, you multiply, so that would be, so 2x is going to be 2, 4, 6, 8, 10, and 12. So you notice the measures of center here are doubled, but it's more, the numbers are more spread out now. The range is now 10 as opposed to 5. You know, the IQR is now 6. When you look at these, the IQR is going to be 6 as opposed to 3. It gets doubled as well. But with X plus 4, what happens? Well, so this is going to be 5, 6, 7, 8, and 9. So compare those to our original untransformed data here. All right, yeah, the measure of center is 4 is added to it. All right, but the measures of spread, by the way, and I think I left a number out here. Yeah, I left out 10. But the measures of spread are exactly the same. Look at the range. They're the same relative to each other. So our range is still going to be 5. Just like it is here. You know, the IQR is still going to be 3 as it is here. They're the same place relative to each other. So therefore, I think I kind of belabored that point, but it's an important concept, and it's a frequent one on the AP Stats exam. All right, what is the effect of multiplying or dividing on a random variable, a measure of center? It multiplies them. It multiplies or divides if you're dividing. Of course, dividing is sort of the same as multiplying in the sense that, like, multiplying by 2 is just like dividing by half, and vice versa. So the measures of center are affected. Measures of spread, same thing. It multiplies them. It multiplies or divides them. Okay, what is the effect of adding or subtracting? It, from the measures of center, are mean and median. It adds or subtracts to them. It affects them. If you add 7, it's going to add 7 to your measures of center. But what about on the measures of spread? It does not affect them. So the measures of spread are unaffected. By the way, other measures of placement, such as, like, let's say the 70th percentile, it would work like a measure of center in the sense it would be added or subtracted to. Okay, or like the 90th percentile, it would be added. If you added 7 to a data set, it would add 7 to the 90th percentile as well. And here's our notation here, that's what that is communicating. If you have a random variable x and you multiply that random variable x by b and add a, that you would do the same with the mean, which is basically what we just set up here. But if you have a random variable x and you multiply it by b and add a to it, it only multiplies it by b, and it'd be the absolute value of b because standard deviation cannot be negative. So anyway, and so here we have our first context here. We have a discrete random variable, just like we talked about in this in the first section. And of course, so this is the number of customers that Lars has his art shop each hour. So sometimes he has 0, sometimes he has 1, all the way up to 5. 22% of the time he has no customers. 3% of the time he has 5 customers. So what is his average? Of course, we could find that. In this case, it told us that, but you would just multiply those just like we did in the last section. And if you need to know how to do that, then watch the 6-1 video. All right, so there's the mean and the standard deviation. If he makes $20 for each customer, what is the mean and standard deviation of his revenue? Well, if he makes $20 for each customer, so that means like when he has 5 customers, that'd be $100. And so that happens 3% of the time. If he has 4 customers, well, that would be $80 and so forth. So what would be, in essence, the new mean? Well, it's multiplying it by 20. So this is, in effect, just 20x. And so the new mean and standard deviation, so would be, our new mean is just multiplied by 20. And so that is going to be 20 times 1.75, and that is equal to 31.4 customers. Our standard deviation would also be multiplied by 20, so that is going to be 20 times 1.2748, and so that, in fact, would be equal to 25.496, just multiplied by 20. Then it says this: Lars must subtract $7 in expenses for each customer he has each hour. What are the mean and standard deviation of the profit? 20x minus 7. So now we're just subtracting 7 from it. So as we discussed up here, that will not affect the standard deviation, okay, but it will affect the mean. So our notation here, the mean of 20x minus 7 is just going to be the 20x, 31.4 minus 7, and so our new mean is 24.7 customers. But our standard deviation of 20x minus 7 is not affected by the minus 7, and so it is still 25.496. So that is just demonstrating that. So that is transformations. The next thing, and so we really had that earlier in the year. But then the next thing we're going to have, we did not, and that's when you're combining random variables. And you say, what do you mean by combining random variables? Well, let's say, for instance, just to give you a quick little example. Let's say you have someone and they own a store and they make money from selling shoes and selling hats. So, and let's just say the amount of money that they make selling shoes, let's just pretend it follows an approximately normal distribution in a mean of $700 and a standard deviation of $20. Let's say in a given week, they make $700 on average, but it varies by the normal curve. So that's our mu, and that's our sigma for that. And so that's, we'll call that mu sub s, and then mu sub for shoes, like that. And then he also makes money from hats each week. And so let's pretend that also follows a normal model, and it's a mean of 500 and a standard deviation of 10. Okay, so there's the mean amount of money from hats. There's the standard deviation from hats. And the question is, what is the total amount of money? How does it vary? And that is what combining random variable means. It means we're going to add them and we potentially are going to subtract them as well. All right, so the total, and so that would be S plus H, our new random variable S plus H. And when you add together two random variables, you can add their means. And so it would also, when you add together two normal curves, it's also a normal curve. Our mean is what you would expect it to be, which would be you just add the means. But here's the thing that's new, is we are going to, first of all, we have to have a stipulation here to do this, if S and H are independent. Okay, so we have to be given that they're independent. In other words, that the occurrence of one is in no way associated with a change in the other one, which may not seem that reasonable here, because if he has a lot of customers, he's probably more likely to sell both more shoes and more hats, but we'll just have to assume that in this problem. So it has to tell us they're independent. We add their variances. Their variances. We cannot add their standard deviations. Of course, the variance is the square of the standard deviation. And this is really, in my opinion, why the variance exists. You say, well, why do we even need the variance? What does it tell us that the standard deviation doesn't? Well, the reason we need the variance is because we can add it when we are adding or subtracting random variables. And so the variance of our shoes, you just square it, is going to be 20 squared, which is 400. All right, and then the variance of our hats, you just square that, and so that's going to be 100. And so the variance, standard deviation squared, and so the variance here, the variance of shoes plus hats is going to be 500. That means the standard deviation is going to be the square root of 500. There you go. That is the main sort of new lesson that's in 6.2. Is you cannot add the standard deviation. You have to add the variances, but you can only do it when they're independent. By the way, if they weren't independent, there's actually a formula that we could use for that, but it's not in the AP Stats curriculum. It contains this correlation coefficient called rho, and it's not that hard to use, but like I said, it's not in there. It's not in this curriculum, so we'll only add or subtract random variables that we know are independent. If they're not independent, then we're just, in effect, not going to worry about them. But that is a potential question that could be asked of you. It could be, say, why can't we add these two random variables? And you could say, well, because they're not independent. All right, so we can't add their we can't add their variances. All right, or it could say, why are you able to add the variances in this problem? Well, because the variables are independent, so that allows us to do that. So that is a common question. Okay. Now here's the notation. In essence, for that, is that, when you're adding two random variables or subtracting, you can just simply add or subtract their mean. So the mean of x plus y is mu of x plus mu of y. The mean of x minus y, and we'll look at that. Actually, we're going to deal more with that in the next video. But the mu of x minus y is the mu of x minus mu of y. And then you always add the variances, okay? If two random variables are independent, you can add or subtract the random. If you add or subtract the random variables, you add, never subtract. And that's the other thing, is you never subtract the variances. And we'll kind of talk about that a bit in our next video as well. So if you go x plus y, you add the variances. But even if you go x minus y, you would add the variances. And so that can seem a bit counterintuitive. But anyway, so let's look at some examples of the type of things that you'll be expected to know how to do. And so here we go. It says the number of calories in a bowl of cereal that Sven each day is approximately normal, and so it has a mean of 120 and a standard deviation of 5. So that's the number of calories from the cereal. So I'll call that C for cereal. It says it varies approximately normal, and our mean is 120, and our standard deviation is 5. All right, and then it says the number of calories from the milk in the bowl of cereal is approximately normal with a mean of 55, standard deviation of 7. So I'll call that random variable M for milk. It's approximately normal, mean of 55, standard deviation of 7. Assume that these two variables operate independently, which, by the way, may not make intuitive sense here, because I would think that the more cereal he adds, the more milk he's going to add. But for the sake of doing this problem, we are going to assume they do operate independently. Describe the distribution of the total number of calories. Okay, cereal plus milk. So cereal plus milk, we're going to add these random variables. And so when you add together two random variables, it will make an approximate, when you add together two normal distributions, it's going to make a normal distribution. The mean, you just add those up, it's 175. But guess what? We cannot add their standard deviations. We have to add their variance. So the variance of the cereal is going to be 25. The variance of the milk is going to be 49. And so thus the variance of cereal plus milk is going to be 25 plus 49, which is 74. That means the standard deviation of cereal plus milk is the square root of 74. That is the big sort of trick of this section. And then after that, we'll just be asked kind of your stock normal problems. So if you were to randomly select one of the bowls of cereal, what's the probability that there'll be a total of more than 190 calories? Well, so we'll just say normal CDF. Of course, you could be asked to draw the normal curve and shade it properly, find the z-score, but we'll just do normal CDF with proper labeling. So this would be more than 190, so that'd be 190 to infinity. So that is my lower bound. That is my upper bound. Mean of 175, standard deviation, the square root of 74. Label that as mu and that as sigma. So, and when we use our calculator to get that, let me remind you how to use your calculator to do normal CDF, which we've been doing all year. So we will go second distribution, normal CDF. Distribution's right above the VARS button there. So second distribution, normal CDF. We hit enter, and so we are going from 190 to infinity, which is just one EE99, or you could just put like, a million there or something. That would work. And so this would be 175 for the mean, and the standard deviation is the square root of 74. The square root of 74, and so that in fact is going to equal to 0.04. So that's 0.040604 right there. So it's kind of unlikely to happen that you would get that many calories. It happens less than 5% of the time, so we would say that is statistically significant that is not going to happen. But anyway, so that is adding together two random variables. And so now let's take a look at another problem. So we've got Anita. So Anita makes money each week by selling cakes and pies. So the amount of money that Anita makes from baking cakes each week follows an approximate normal distribution, mean of 400, standard deviation of 70. So I'll call that C for cakes. So C for cakes, it's approximately normally, mean of 400, standard deviation of 70. The amount of money that Anita makes from baking pies each week follows an approximate normal distribution with a mean, so that is also approximately normal, a mean of $500 and a standard deviation of $60. All right, the amount, okay, and so assume that the money from cakes and pies are independent. That allows us to add the variances. You can always add the means, by the way, whether the variables are independent or not. But anyway, so if you randomly select a week, what's the probability she makes a total of more than $1,000? Cakes plus pies. So we'll just say normal. So, well, first of all, cakes plus pies, this new random variable, cakes plus pies, it will vary approximately normally. Our mean is going to be 900. And our variance here, so our variance of the cakes is going to be 70 squared, which is 4,900. Our variance of our pies is going to be 60 squared, which is 3,600. And so we can add those. So the variance of our cakes plus pies is going to be equal to 8,500, I believe. And so therefore, the standard deviation of cakes plus pies is the square root of 8,500. That is the main part of this section. And so now we can do a total of more than 1,000. So we would say normal CDF from 1,000 to infinity, mean of 900, standard deviation of the square root of 8,500. And so that is our lower bound. That is our upper bound. That is our mu. That is our sigma. And that, in fact, is going to equal to, let's see, that is going to equal to 0.139038. So there we go. So that is adding random variables. We will come back now on the next video, and we're going to look at some of the tougher problems in the section in regards to subtracting and that sort of thing. So I will see you in the next 6-2 video. Thank you for watching.